Good afternoon, everyone, and welcome to the Amherst Women's Club meeting. I hope you all are doing well and are looking forward to Thanksgiving, even though many of us will be celebrating it in a different way. Our guest speaker this afternoon is Dr. Michael Rawlins, who will be talking with us about climate warming and climate change. His credentials are quite impressive, so I'm going to read them. Dr. Michael Rawlins is Associate Director of the Climate System Research Center and Extension Associate Professor in the Department of Geosciences at UMASS Amherst. His research focuses on advancing understanding of the hydrology and biogeochemistry of Arctic environments. His research often involves application of numerical models to investigate how climate processes influence terrestrial water and carbon cycles, and the ways in which warming, permafrost thaw, and hydrological cycle intensification are impacting life across the northern high latitudes. Dr. Rawlins frequently engages with news media to communicate the local and broader scale impacts of our warming climate. Welcome, Dr. Rawlins.
Thank you, Beverly, for that very kind introduction. Hello, everyone. Thank you for being here today. I want to extend my sincere appreciation and gratitude for having this opportunity to speak with you today. As Beverly was mentioning, my research is focused largely on the hydrology and carbon cycle of Arctic environments, but I do engage in research a little closer to home, trying to understand how much our climate is changing and how much we'll likely see a climate changing in the future. For example, how much warming we may see, precipitation changes, and other climate impacts across the Northeast US. Okay, let me just realize I don't yet have my presentation opened up. So just give me a moment here. Okay. Is my screen being shared right now? Okay, I'll do that. Excellent. Okay, so I'm speaking to you today about understanding the causes and consequences of climate change. And as I mentioned, we're going to start local here, and then I'll broaden out and speak to you in general about how we understand climate changes and the differences between natural climate cycles and human-induced climate changes that we're experiencing. And then I'll bring this back a little closer to home about some future changes we're likely to see here in, let's say, the greater Amherst area or Massachusetts in general. And then a few take-home messages about how we have some opportunities to change the way our energy is being generated and in order to reduce greenhouse gases in the atmosphere and eventually reduce the warming we'll see in the future. Many of you probably recall that we had a really warm summer here in Massachusetts. This chart here is showing summer temperatures. So the average temperature for the months of June, July, and August is averaged across the state of Massachusetts. So what this is showing here is you can see 2020 here was the warmest summer on record for the state of Massachusetts. This is a time series that extends back to 1895. And what you can see here is a clear warming trend, a significant warming trend. So if we test this time series for statistical significance, we know that this increase in temperature is beyond just simply chance. And you can see here clearly that if we look at 70 degrees temperature before 2000, there was only, I should read 2000, before the year 2000, there was only 1 year, 1949, that was warmer than 70 degrees Fahrenheit. Since the year 2000, there have now been 6, with 2020 as the record warm summer. So it's clearly warming in summertime in Massachusetts. The warming we're seeing, it's also expressed locally and seasonally. So if we drill down and just look at temperatures for Amherst, and these are time series here going back to 1836. Amherst, interestingly, has one of the longest climate time series in existence in the United States. So back in the 1830s, a fellow named Ebenezer Snell made a lot of measurements here near Amherst College. The locations of where the temperatures are recorded has since changed, but if we look at something like a seasonal temperature, that change in distance, that change in location doesn't really have much bearing. So you can clearly see for Amherst, winters are getting warmer. And notice this chart on the left here, the warmest winters now, these last few winters here that are the warmest since around 1980 or so, they're now over 32 degrees Fahrenheit. So think about that for a moment. Our warmest summers or our warmest winters our winters are tending to be in the last few years above the freezing mark. That has really big implications when you think about it. The average temperature for winter is now above freezing during the warmest winters. Okay. We could also see that fall has been warming. This only extends to 2016, but it's very clear that we can see this warming across all seasons and also locally in Amherst. If we extend out and look at global temperatures, so globally average temperatures, this is a time series, a lot of different curves here and colored curves. These are all different estimates of temperature made by different organizations. And what is really clear from this view of global average temperatures going back to 1850 is this really sharp warming we're seeing since around the 1970s. There was often, we refer to this period in the 1950s and 1960s as a warming pause. If we go back, let's say back to the early 1900s, this warming pause has various influences that we think that caused that. Most likely it was due to all our use of fossil fuels, a dimming of the skies, essentially, with all the pollution. We've now cleaned up our air, and you can see here very clearly this really strong warming over the past 60 to 70 years. It's without doubt that the climate is warming. Okay, now what is the cause of this warming? We believe it's human activities. And that's because if we look at time series of global averaged atmospheric CO2, carbon dioxide, what these charts are showing is the amount of carbon dioxide in Earth's atmosphere measured at Mauna Loa in Hawaii. Why do we look to Mauna Loa for these records of atmospheric CO2? Well, one thing is it's in the middle of the Pacific Ocean, far away from any industrial sources. If you were to measure atmospheric CO2 levels here in the Northeast US, you're going to get a lot of the signal from the power plants to our west. Okay, so Mauna Loa is a great place to give us a relatively clean look at what's the amount of carbon dioxide in the atmosphere. And then it's also up above, up at some altitude where it's the variations essentially are a little bit less strong. So you're getting a really good idea of what's a general amount of carbon dioxide in the atmosphere if we were to look and think about the Earth as a whole and not any one specific point. What these charts are showing here is this one on the left here is going back about 6 years. And you can see these red lines are wiggling up and down. Well, this is our seasonal cycle in atmospheric CO2. So essentially, when you see this red curve going down, that's in our spring and summer when the Northern Hemisphere, you can think about leaf out. Think about here in Amherst, when we get to March, April, and May, and the leaves all come out of the trees. Well, that carbon is being created, that's photosynthesis, that's fixing and taking carbon dioxide out of the atmosphere, and plants are fixing it and creating carbohydrates and essentially solid carbon in these organisms, if you will. Right? So this is showing the drawdown and then the increase in the winter time, fall and the winter. You think about all the leaves that are out here right now. All these leaves are going to decompose, and that's going to be carbon dioxide going back up to the atmosphere. But unfortunately, the ups are bigger than the downs, so you see this tendency for this trend going up. And that's shown clearly in this chart on the right, showing the record at Mauna Loa extending back to the late 1950s, when a fellow named Charles Keeling began to make measurements there at Mauna Loa. And this shows a very clear upward trend in atmospheric CO2. There's been essentially approximately a 45% increase in atmospheric CO2 going back since the levels around the beginning of the Industrial Revolution, which were about 280 parts per million. Now we're looking at the totals here for atmospheric CO2 right around 410 parts per million as of a couple months ago. Well, so how do we know whether these increases in CO2 and decreases, how do we put this into some longer term perspective? Well, we can do that by looking at ice core records of greenhouse gases, GHGs. So this chart on the right is showing us atmospheric carbon dioxide here in red, going back to approximately 2,000 years ago. And what this shows is that atmospheric CO2 was very, very stable, extremely stable, right around 280 parts per million for all that time. And then it increased very, very sharply here toward the end of the record. And that's showing the carbon dioxide in the atmosphere accumulating after the beginning of the Industrial Revolution, essentially the last, let's say the last 150, 200 years, where this sharp increase. So we know that greenhouse gases, and also you're looking at methane here in blue, carbon dioxide again is in red, and nitrous oxide. These are all greenhouse gases. The atmosphere was essentially not changing much over these 2,000 years and only increased toward the end of the record. That atmospheric CO2 concentrations the time series essentially, it looks a lot like this record of northern hemisphere temperature going back around 1,000 years. This time series is going back 1,000 years. So think about here, year 1000, stable, and then a sharp increase in greenhouse gases. Temperatures going back 1,000 years, very, very stable, very, very slight cooling. Think about the little ice age here, 14, 15, 1600s. And then the temperatures increase sharply just over the last few hundred years. Okay. So this tells us that there looks like there's a really good agreement between what the atmosphere greenhouse gases are doing and what northern hemisphere temperatures. Now here we know that the atmosphere has greenhouse gases, and many of you probably are aware of the greenhouse effect, where the Earth is receiving radiation from the sun. The surface heats up, land, oceans, and then the Earth is radiating long-wave radiation that gets absorbed by the greenhouse gases and then retransmitted to the surface. If we didn't have these greenhouse gases in the atmosphere, our Earth would be too cold to be habitable, essentially. We'd be looking at temperatures around 0 degrees Fahrenheit for a global average. We would have a much different Earth without the greenhouse effect. So the greenhouse effect makes our planet habitable, but when we increase these greenhouse gases, it looks like that tells us that the Earth should warm. And this was something that was put forth by a fellow named Arrhenius back in the 1800s, who posited that an increase in greenhouse gases would warm the Earth. And this chart here is called the hockey stick, published by Mann, Bradley, and Hughes, Ray Bradley from the University of Massachusetts, back in 1998 and 1999. Well, what about ice ages? So we know that there's ice ages. We believe we have records, geological records that tell us that the Earth went through ice ages periodically and then warm interglacials back and forth. Well, what drives those? Well, we're almost certain that what drives those are these periodic, very slow changes in how the Earth orbits around the sun. There are 3 cycles referred to as Milankovitch cycles, after a Serbian astronomer who deduced that these very slow changes in the Earth's orbit have an influence on the amount of radiation received over parts of the Earth. So these charts are showing us carbon dioxide. I should mention those greenhouse gases that we looked at in the previous slide, going back 2,000 years. We get those by drilling an ice core in large ice sheets on Antarctica and Greenland. And they take an ice core, and the ice core, a big long cylinder of ice, hundreds of feet, hundreds of meters long, has bubbles in it. And those bubbles are little bubbles of ancient air that were sequestered, if you will, in the ice when the snow fell. So you have air between the snowflakes, and that gets compressed to ice. We take those bubbles in that ice core, extract those bubbles, and then test that for greenhouse gases. We can also do that with this longer ice core going back 800,000 years from Antarctica. So what this shows, if you notice these wiggles up and down, these look very similar to the temperature records that we get from that ice core. Again, another gas, an isotope of hydrogen, tells us about the temperature. So if we take those bubbles of air, look at the carbon dioxide in those bubbles going back for the part of the ice that's 800,000 years old, compare that with temperature, we see the wiggles seem to match. So this tells us that as carbon dioxide concentrations in the atmosphere increase, it gets warmer. When carbon dioxide goes down, Earth climate gets cooler. This makes physical sense. This is basic physics. So these slow changes in Earth's orbit cause these ice ages and warm interglacial periods. The changes in these orbital parameters are minimal, insignificant over the last few thousand years. These orbital changes, they're so slight that they cannot explain the warming we've seen over the past 150 to 200 years. So when someone says, oh, well, we have ice ages all the time, it gets hot and cold, well, we understand that. Those are natural variations in the Earth's orbit that cause these ice ages, cannot explain the recent warming that's happened over the past few hundred years. Another way we can learn how we have evidence that natural factors alone, natural forcings, we call them, on Earth's climate, cannot explain the warming. So this is essentially a chart that shows this black curve here is the observed temperatures going back to 1900. So you see this, again, the sharp warming over the past 5 to 7 decades, 50 to 70 years or so. The red curve is natural, the natural forcings alone, volcanic emissions and the solar cycle, the Earth's, the amount of solar radiation put out by the sun. We know that varies slightly over 11-year time scales, the 11-year solar cycle. If we look at just the natural forcings, volcanoes and solar cycle, that's shown in blue. You see that does not go up like the observed temperatures do. It's only when we take the natural forcings, volcanoes and solar cycle, and add in the greenhouse gases, that's the red curve. Now that matches up closely with the observed temperature observations. So this shows us that when we run a model and force it with just natural factors, the temperatures do not warm. It's only when you use your model, including human activities, greenhouse gases, that then we can match the observed warming that we see. So this is a piece of evidence that tells us that natural variations in climate forcings, volcanoes and solar, cannot explain the recent warming we've seen. There are also many indicators of a warming world. So we have many pieces of evidence that tells us that the Earth is warming. Start on the left here, sea ice is declining. Sea surface temperatures are going up. the amount of heat content in the oceans is increasing. Sea level is rising. We're seeing more water vapor in the Earth's atmosphere. Air temperatures are increasing in the atmosphere. We see a decline in land of glaciers and ice sheets, a decline in snow cover across land, and temperatures where we measure them on land are going up. All these are indicators of a warming world. We're seeing all this changes based on evidence we see out in the real world. Well, when we talk about changes in the Earth's climate, for example, let's say an increase in the average temperature, what happens when we have an increase in the average temperature, that's essentially shifting this distribution, and that will result naturally in more record hot weather. So not only is average temperatures increasing, but that's influencing these hottest extremes of weather. If we look at records of high temperature records and low temperature records, we can see that the climate is not stationary. So if the climate was stationary, you'd see an equal amount of record highs and record lows set in any given year or 10-year period. And that was the case back in the 1950s and the 1960s. It was around 1-to-1. So you'll hear oftentimes about, say, a record high temperature set or a record low. We had the warmest summer on record. Some folks you'll also point out, oh, we had a record cold month or a record cold day. Some skeptics may say, look at this record cold. The climate can't be warming. We had a record cold day. Not true. We look at the ratio, how many record warm records are set relative to cold records. And in the past several years, we're seeing a 2-to-1 ratio of record highs set to record lows. And that tells us the climate is not stationary, it's warming. So we can't let anybody tell us that just because we see a record cold month or a record cold day, that the climate's not warming. Have to look at the record highs as well. I mentioned that the oceans are gaining heat. The oceans have many fewer observations. It's a lot harder to understand the oceans than it is temperatures on land. Nonetheless, all the observations show us that our oceans are warming. And if we look at the amount of energy coming from these increasing greenhouse gases in the atmosphere, where is that energy going? Much less of that energy from the increasing greenhouse gases in the atmosphere is going into, let's say, warming the land or end up warming the atmosphere or melting ice. Most of that energy is going into the ocean. The oceans are warming up. The oceans can gain a lot of heat. They can store a lot of heat. So the upper ocean is the part of the Earth atmosphere system that is gaining the most heat energy from the forcing from the increasing greenhouse gases. And what happens is essentially all this warmth going into the oceans tends to emerge, if you will, periodically, let's say when we have an El Nino. So what the Earth is essentially doing is it's taking a lot of that energy from the increasing greenhouse gases, warming the land, melting ice, but mainly warming the oceans a lot. And then periodically when we have an El Nino, we get a really warm global average temperature. Unfortunately, what we're seeing right now is we're also seeing record warm. We're seeing a very warm year here in 2020 when there's actually the opposite. It's a La Nina going on in the Pacific Ocean right now, cooler than average temperatures in the Pacific. So bottom line here is the oceans are absorbing a lot of heat, and that periodically emerges and results in a record warm year, if you will. Well, those warm oceans are having an influence in other ways as well. You may have heard a lot about the record-setting hurricane year. You see on the news the past few months, there's a hurricane almost every week, a really strong hurricane as well. Well, we know that ocean waters around the world have warmed by around 1 to 3 degrees Fahrenheit over the past century. And that's including in regions where hurricanes develop. So hurricanes and climate change. Warmer water equals more fuel for hurricanes. Also means that we'll see heavier rain and higher storm surges. So essentially the atmosphere can hold more moisture when it's warmer. And that's just a basic, that's a basic law of physics, if you will. Warmer atmosphere can hold more moisture. Our atmosphere holds more moisture in the summer than it does in the winter. So all that moisture in the atmosphere, occasionally when the storms come through, can rain out. And so we're seeing it's approximately a 4% increase in water vapor in the atmosphere for every 1 degree Fahrenheit increase in temperature. So climate change can lead to heavier rain from hurricanes and increased coastal flooding due to storm surge. Evidence suggests that hurricanes are intensifying more quickly now than they did 30 years ago. As I mentioned, there was a record-setting 2020 Atlantic hurricane season. The season's winding down quite naturally because the ocean waters are starting to cool. We're well past the summer solstice when the radiation is most intense in the northern high latitudes or the northern hemisphere, third week of June. Right? So ocean waters are cooling, the season's ending, but there have been 30 named tropical storms and hurricanes in the Atlantic in 2020, the most on record. 10 of those storms experienced rapid intensification, which is by definition a maximum sustained wind increase of at least 35 miles per hour in 24 hours. So this was a very devastating hurricane season, several landfalls in Louisiana, also in Florida. As you may have heard in recent weeks, Nicaragua and Honduras has been devastated by 2 major hurricanes, one Category 4 and one Category 5 just last week. This is evidence that the climate is warming as well. We believe that as the climate continues to warm, we may not see more storms, but the evidence suggests and the modeling suggests that we'll see more intense hurricanes like what we saw this year. I mentioned sea ice. Sea ice is declining in the Arctic Ocean. So Arctic sea ice extent, this is ice floating in the ocean, for October 2020 was the second lowest in the 42-year satellite record, behind only September 2012. So this time series chart on the left is showing us monthly average. So apologies here, I've got a September chart and an October statistic here, but the September chart here of sea ice extent, just like the October sea ice extent would show us, is this really precipitous decline, really very sharp decline in the amount of sea ice in the Arctic Ocean, right? So going back, the beginning of the satellite record here for Arctic sea ice extends back to around 1980. So back in the 1980s, the Arctic in September used to see about 7 million square kilometers of sea ice. That's shown here in the map on the right. And now in the past few years, it's more like getting down closer to 4. So it's approximately a 50% decline in the extent of ice here in September. And that's when sea ice extent reaches its minimum for the year. It's right around the end of September. So we can see September sea ice extent in 2020, shown in the white here, was much lower than the climatological long-term average 1981 to 2010 average, which is shown extent by the pink line here. So sea ice is declining. That's another indication that the climate's warming. Not a long record here, but nonetheless a very, very steep decline in the amount of sea ice in the Arctic Ocean. You could think about here, we hear about polar bears struggling. If the polar bear here wants to get out to the sea ice to hunt, it's got a long way to swim here to go from northern Alaska to reach the sea ice here. Now it's going to grow back in the winter and start reaching closer to the Alaska coast. But with this low extent here in September, it's likely we'll get into the midwinter, late winter, and still not be back to what was normal 3 or 4 decades ago. And that sets us up for even more loss next spring and summer when the sun starts to emerge in the Arctic again, after the dark Arctic winter. I mentioned warming. Well, this warming that we're seeing is not evenly distributed across the globe. This is a map that shows the temperature change in the last 50 years, with the areas that are warming the most shown in this darker orange color, and much less warming here in the white and yellow. And what this is showing us is that the Arctic is warming around 2 to 3 times as much as the global average temperature. So I showed you earlier a chart of a time series that showed global average temperature. That's the average for the globe. The Arctic is warming much, much more than the rest of the globe. And that's because the Arctic is full of ice and snow. And as we warm, we're losing ice and snow. And that snow and ice has a very high albedo, high reflectivity. And so it reflects away a lot of the sun's energy. Think about when you go out, if you go out skiing and the sun's shining and you don't have sunglasses on, hard to see, you're getting blinded by the light, if you will. Well, as the Arctic and northern high latitude lands lose snow and ice, it's exposing darker surfaces that absorb more heat. That warms the climate more and we lose more snow and ice. And that's a vicious cycle called a positive feedback. The tropical oceans are warming the least. The northern high latitudes, as we might assume based on simple understanding of albedo and reflectivity and warming, Arctic is bearing the brunt of the warming that we're seeing over the past recent decades and century. Some more observations of recent changes. Now let's bring this back a little bit closer to home. Let's focus here now on the Northeast US. Precipitation is increasing. So annual precipitation average across the Northeast US has increased over the past 100 years from right around 40 inches per year to more like around 46 inches based on this linearly squares trend line. And you could see some of these years, we had a few years here in the recent past 10 years or so that had upwards of 55 inches of precipitation. Think about the year 2018. 2018 here was the second wettest year on record for the Northeast US. So we have a time series increase showing that it's getting wetter. Precipitation is increasing. That's consistent with a warmer atmosphere that can hold more moisture. And along with this increase in annual total precipitation, we're seeing more intense events. In 2018, a lot of locations in this area saw upwards of 24 days a year in the year that had more than 1 inch of precipitation. That was a record as well. So not only more total annual precipitation, but more extreme events. We're seeing the warming here over Massachusetts is not even, if you will, across all seasons. Winters are warming more than the other seasons. And that's again consistent with our understanding of losses in snow and ice. Darker surfaces resulting in more warming in winter when we have less snow cover. I should mention that the Northeast US and the Great Lakes region, all the states in the Northeast and the Great Lakes are showing this warming is greatest in the winter season. I mentioned very heavy precipitation events. The Northeast US has seen approximately 71% increase in the heaviest precipitation events. So think of, let's say, the number of days each year when we have 1 inch of precipitation and above. The Northeast is seeing the greatest increase in these heavy precipitation events out of all the regions in the United States. This is interesting to note here that the Southwest US is seeing a 5% increase in the heaviest precipitation events during a time when annual total precipitation is decreasing in the Southwest US. So annual total precipitation, it's getting drier essentially in the Western US, having a lot of issues with fires and also with water resources, less snowpack in the Sierra Nevada in California and the Rockies in Colorado. But with this decrease in the annual total precipitation, they're seeing an increase in these heaviest events. So what you're seeing essentially is some days of the year it'll rain a lot, this heavy intense event, 1-2 inches of precipitation, and then a longer period without rain. And that's consistent with our understanding, again, of a warming climate that holds more moisture while it warms. Just mention quickly that we're seeing a shift in the amount of runoff, essentially river flow in the rivers in the Northeast US. And what you're seeing here is these are showing higher runoffs in March and lower runoff and river flow in May. So that's indicating that the amount of water that's flowing in the rivers in the springtime is shifting. The peak flow, let's say the peak flow of the Connecticut, is shifting earlier by several weeks in the year. So normally we'd see the Connecticut River after snowmelt was at its highest for a daily flow in the Connecticut. Highest, used to be highest in, let's say, sometime in the middle of April. Now it's shifting to early April or late March. And that's because snow's melting earlier as the climate warms here in the Northeast US. So what about future changes? What can we expect here in Massachusetts and the Northeast US in general? These are maps that I made for a paper that I published in Journal of Geophysical Research in 2012 that's showing projected changes in seasonal air temperature. So winter average temperature, spring temperature, summer, and autumn. So this is projected for the period 2041 to 2070 relative to some baseline period from late last century. And what this is showing us is warming is predicted by models. So these are climate models. The warming is predicted to be greatest in winter, shown here in the red. These climate models suggest that over Western Massachusetts and parts of the Northeast US, and here in red, upwards of 3 degrees Celsius, around around 5 degrees Fahrenheit warming in winter by mid to late century. And warming in winter will be greater than any of the other seasons. Okay. This is again consistent with our understanding of declines in snow cover in winter. And these same models project that winter will get wetter. The other seasons, there's some uncertainty, and perhaps the models are suggesting that in summer it may get drier across Pennsylvania, but the models are a little bit less certain in the other seasons, perhaps a wetter in springtime, but clearly they're showing that winters will be wetter by around 10 to 15%. Now, this doesn't indicate that there will be more snow necessarily, just more total precipitation, snow and rain combined. So looking forward, how does the warming over the Northeast US projected by these models compare to the global average warming? And for warming projected by the models to occur across other parts of the US? The models are unfortunately suggesting to us that the Northeast US is and will continue to warm more than other parts of the US and much more than the global average temperature. If we want to look at the models and say, okay, when do we reach 2 degrees Celsius warming above, let's say, pre-industrial temperatures? Well, these models suggest that the Northeast US will hit a 2 degrees Celsius warmer than pre-industrial temperatures around 2040, approximately 20 years earlier than the global average temperature reaches 2 degrees Celsius. So this tells us that we are essentially kind of leading the pack. The warming that we're seeing over the Northeast US is greater than the global average warming we're seeing. Now, if you were to plot on here temperatures for an area in the Arctic, that would be even more sooner. The Arctic is essentially warmed by now above 2 degrees Celsius already, given how much the Arctic has warmed more than even the Northeast US and the rest of the globe. So we're kind of, it's likely that we'll see some of these more troublesome impacts across the Northeast US than perhaps other parts of the globe. We're seeing that the warming that we're projected to seeing in the future is essentially based on how our emissions, how our activities, human activities, impact the emissions of greenhouse gases. I'm not going to really go much into these charts here, just to say that we developed these scenarios of how the Earth, how our human behavior will change the amount of greenhouse gases in the atmosphere. So under the higher emission scenarios, let's say that less renewables come on board, more burning of dirty coal, dirty fossil fuels, global average temperatures may reach 8 degrees Fahrenheit warming by the end of the century. However, if we act in order to limit the amount of warming, if more renewables, less deforestation in the Amazon, less reductions of those sinks of carbon, we're likely to see much less warming. So this tells us that our future is in our hands, that our activities have a strong bearing on how much warming that the global average temperature will see in the future. So naturally, when we see a warming climate, that means a shift, let's say, in how it feels across Vermont, Massachusetts. And what we can do is we can run these scenarios saying, okay, under the moderate lower emission scenario, the temperatures across Vermont or Massachusetts will feel more like Pennsylvania or West Virginia's current climate by the middle of the century. Under the higher emission scenario, the folks in Vermont, by the end of the century, it will feel more like it does in Northeast Alabama, Northern Georgia, than what we're typically accustomed to in Vermont. So this is a way to kind of display how things will feel under the different emission scenarios that will be realized in the future. I mentioned snow cover is declining. By the end of the century, the area under snow cover in the Northeast US will likely be confined here to the number of days that has at least 30 days of snow, will likely be confined to the northern parts of New York, Vermont, New Hampshire, and Maine, versus the red area showing our historical area that has more than 30 days of snow in a given year. So this is likely problematic for many reasons, not the least of which will be for ski resorts in the Northeast US. I mentioned that we're seeing sea level rises. Well, sea level has been increasing across many parts of the globe, and it's also increasing across areas near where we are here. So sea level rise across the eastern US has been around about 1 foot over the past 100 years. This is a time series showing the sea level rise, observed sea levels near Philadelphia, showing about a 1 foot, again, 1 foot increase in sea level rise across parts of the eastern US. Slightly more to the south and slightly less up here in New England. But sea level is a problem. Under the higher emissions scenario, by the end of the century, sea level rise can approach up to almost 1 meter. This is almost 3 feet of sea level rise by the end of the century under the most worrisome emission scenario. Okay, and this is global average sea level rise. This will be different in other different parts of the world, depending on where you are. But we can imagine that a sea level rise of 2 or 3 feet could be a really problematic for a lot of folks living near the coast. We think about Boston area. There are a lot of low-lying areas around Boston. Shown here, these colors are showing different areas impacted, whether we see a 2, 3, or as much as a 6 foot increase in sea level would impact parts of Boston. I'm going to finish up here with a few slides talking about sea level rise, in particular looking at Venice, Italy, and then wrap up with some concluding remarks. In Venice, Italy, Venice has been has felt the impacts of sea level rise they call it their aqua alta. So you can see here, these sidewalks are flooded. You know, Venice is built, it's essentially built on a, what you, if you would call it like a landfill. They filled in the land area. You've got a lot of water surrounding Venice, in and surrounding Venice. And when these high astronomical tides, let's say because of the lunar cycle, occasionally they would have a lot of really strong flooding, aqua alta in Venice. And what they've done in Venice was they've installed these gates, if you will, that can block the amount of seawater that reaches Venice. Understandably, this is quite an expensive system to install. Well, they did this near Venice. And so October 3rd, there was a really, really high sea levels were predicted. So they raised these gates. And this was a typical view during aqua alta of this large plaza in Venice. And after they raised those gates, now it's dry. So they were able to mitigate these high sea levels by installing these barriers around a really small area around Venice, Italy. Well, needless to say that this would be an expensive proposition if you were going to try to protect all of the areas subjected to sea level rise across, let's say, the United States. They're doing this in the Netherlands, and it's billions of dollars just to protect 350 kilometers, around 200 miles of coastline. The United States, it would be extremely expensive, needless to say, to try to put up barriers to block areas of even, let's say, around New Orleans or Miami or any other large city in the US. But there is some reason for some optimism. So over the past 12 years, the greenhouse gas emissions from the United States have been declining. It's a really, really good sign that our peak emissions, that we've reached the peak emissions and that we're able to bring them down because of the use of fossil fuels. So greenhouse gas emissions from the US have been trending down for 12 years due to more use of gas, less dirty coal, more renewables, and greater efficiencies. This year, the US emissions are projected to drop by right around 10%, and that's simply due to the global pandemic. There's less travel. The largest decline from 2009 has been in the transportation sector, and second largest decline in the power generation sector. But this tells us that if we can bring on renewable energy in an ambitious and aggressive way, we can reduce our emissions from the US and begin to get to a carbon neutral energy system. Hydropower from water has been the largest source of renewable energy historically, but as you can see from this chart, wind energy and solar are gaining ground and likely to be a significant source of our electricity generation in the future. Some countries in the world, Iceland, Brazil, are getting a large majority, greater than 80% of their electricity from renewable energy. It's a little more tough to get that in the US, but nonetheless, wind and solar power are both growing very, very rapidly. So to wrap up, just a few summary statistics. Observed changes across the Northeast US between about 1895 and 2011. Temperatures have increased in the Northeast US by about 2 degrees Fahrenheit. The region has experienced a greater increase in extreme precipitation events than any other region in the US. Coastal flooding has increased due to a rise in sea level of about 1 foot since 1900. Other climate changes, we're seeing the frequency, intensity, and duration of cold air outbreaks is expected to decrease. We're expected to see more extremely warm days. Winter and spring precipitation is projected to increase, especially in the north. We could expect around a 5 to maybe as much as a 20% increase in winter precipitation Again, not necessarily more snow. We're likely to see, as the climate warms, less snow and more rain. The frequency of heavy downpours is projected to continue to increase. Snowfall will decline, and it's likely that the area of snow-covered ground will be far less. And projections of precipitation changes are less certain than the temperature increases. And I'll leave here with a pointer to a URL for the Climate System Research Center web pages we have, and a couple graphics, logos showing the Climate System Research Center. Again, we're at the University of Massachusetts Amherst, and I'd be happy to entertain any questions that you may have. And thank you for your attention.
Okay, folks, go ahead and raise your hand. Catherine, go ahead, unmute yourself. Catherine, you'll have to unmute yourself.
Yeah, still can't hear.
There we go. There we go. Okay, wrong place. I was doing it down on the far left instead of the middle.
You can hear
Yes, Dr. Rawlins, you said that the Northeast, that we were warming faster than other parts of the United States. Why? Why are we warming at a faster rate?
Well, most likely causes that in winters, in the colder months here, as much as 3, sometimes as much as 4 months, we're seeing less snowfall. Snow is melting. It's exposing darker surfaces. It's called the snow albedo effect.
Right.
So the Northeast U.S. and then next to the Northeast, the upper Midwest is also seeing sharp warming. So these are the northern parts of the U.S. So you're seeing less warming in the southern U.S. because the southern U.S. has little, if any, snow. So it's the snow albedo feedback, this positive feedback between the amount of snow in an area and temperature. That's resulting in us warming more than other parts of the U.S.
Even the Northwest, which historically has snow, or maybe the mid-Rockies or something.
Not really. Not in the Northwest U.S. No, not in the mountains, but not as extensive in the Northwest as the Northeast. Yeah. Okay. So the snow albedo feedback is much less of a influence in the Northwest because, yeah, as far as extensive area covered by snow, less of the area in the Northwest is covered by snow as compared to the upper Midwest and the Northeast.
So what you're telling me is my bears are not going to hibernate, and they're going to be out hunting for my bird feeders all winter long now.
As the temperatures warm, I would, yeah, that's good. That's an interesting question for biologists. At what temperature do bears? I think there is some evidence that some are hibernating. Bears and other species are hibernating a little bit less time. Yeah. I think that's something. I don't know if that's for this area necessarily, but some parts of the northern latitudes, there is some tendency for these hibernations to be shortened. That is true.
Well, I've noticed different birds at the feeders. I've noticed I have very friendly bears for longer periods of time. So maybe that's some of the animal changes we can expect.
That's likely going right along with they're responding to what the temperatures are like.
Right. Right. Thank you.
You're welcome.
Okay, Susan, go ahead.
Would that be true of some of the diseases that we might experience if the changes in the bears and the changes in the climate not that I'm suggesting it has anything to do with COVID, but I've heard that we will suffer different or new kinds of ailments due to climate change.
Yeah, one thing I like to point to is think about that, the temperatures for the winter average being above freezing. And think about things that die off when it gets below freezing. I always point to things like I'm a little bit on the right word. I'm a little uninformed about the exact biology, but I think about ticks and mosquitoes.
Uh-huh.
Mm-hmm.
And unfortunately, there are actually parts of the U.S. right now that have a very short frozen season. Let's say to our south, and let's say over parts of Kentucky, Tennessee, let's say they only have on average about 30 days or maybe 3 weeks that are below freezing each year. They'll completely lose their frozen season. It will never even fall much behind. And then you think about the impacts on things that are affected when you have frozen versus thawed. And think about an area that never sees below freezing temperatures anymore. Ticks, I think about ticks and mosquitoes. You'll probably have mosquitoes if you no longer have temperatures much below 50, parts of the South that no longer get below 50 or 40 degrees, probably have mosquitoes year round maybe. So a lot of things will be affected when you have temperatures are crossing these thresholds. And I point to that temperature of freezing as being particularly, it's my understanding that that freezing point is very, there's a lot of things that are sensitive to that.
No, thank you. Thank
And in
you.
particular, that's a great question. In particular, it has more of an influence for things that have a very short lifespan. We're more influenced by seasonal temperature changes. Daily temperature changes for more of an influence for something that only lives, let's say, 1 year. So these temperature swings, if you have a record warm year, that's likely to impact something that only lives a year or two very profoundly.
No.
Yeah.
Thank you.
You're
Yeah.
welcome.
Okay, Dorothy has raised her hand. Go ahead, Dorothy.
So my question is about agriculture. My daughter's a farmer, and I know that my son-in-law says it's easier to put water in than to take water out. So they've been very busy making sure that they have wells and irrigation on all the land they own or lease. But if we're getting to be, we had a really wet summer a couple of years ago, and it was really bad. A lot of products, a lot of things just kind of like did not come out well. So what is your prediction for agriculture in the Northeast in Massachusetts?
Yeah, I remember that what you're talking about is the summer and fall of 2018, 2 years ago. The farm fields were flooded, right? That was a record, nearly that record wet year. So with this water cycle intensification, this change toward this wetter years that we're seeing here in the Northeast US and in Massachusetts, right? I showed that time series of some years we're getting close to 50 inches. You can't take the water out of the fields as you mentioned. So as far as precipitation, I would think that there may be a problem with farm fields flooding in the future if we continue to get wetter. Now, the temperature changes, they're also going to see some impacts as far as if you have a really, really warm summer, and let's say some particular crop may not be able to handle 2 weeks straight of temperatures over 90 degrees or 100 degrees or something like that, some specific threshold. Certain crops can tolerate a little bit more heat, some can't. So farmers in this region have to obviously pay really, really close attention to what the projections for temperature changes are going to be like, and whether the crops, if the crops they're growing right now may be reaching a point soon where they're no longer viable, they may have to switch to some crops that do better under warmer conditions. So that's something that they're going to keep a really close eye to. I recall I have to go back and look at it. It's something about tomatoes, and I can't recall if tomatoes are particularly hardy enough able to tolerate heat or not. They're at one end of the extreme. And I can't recall what that is, but as you mentioned, the precipitation change that we're seeing, and I spent a lot of time in the fall of 2018 interacting with news media. There's some really, on my website, I have all the articles are linked, And in the fall 2018, I was interviewed by the Daily Hampshire Gazette, NPR radio. There was a lot of organizations reaching out because we were so wet, and I was sharing information with the news media saying, okay, this is a problem. It was one great opportunity for where we were able to take our understanding of how the climate is changing and how that's directly impacting people in our local area. That was what was very, very clear about our outreach during that time, was we were linking and making it clear that climate change is not something that's far off that we'll see and experience in the future. That's no longer the case. We're seeing the impacts of warming and associated climate changes as we speak. It's not something in the future.
I just wanted to add one thing. They've done some weird things, such as plowing in February. They're putting crops in, many of the farmers around here putting them in at weird times.
Weeks earlier.
Weeks earlier, maybe months earlier. And a lot of farms around here are doing more of the hoop houses, and we're getting into year-round farming. So it is, you're right, farming it's very scientific now. And they do use, what are those little drones? They use, satellites and what to see what's going on with the weather. So it's a crazy time.
Yeah, that's a very, very great comment. And what was that point? Oh yeah. Had a comment there, and I'll see if I can resurrect it. Yeah. I'll take another question if there is one.
Go ahead, AJ.
Oh,
A question on the trees, when you were talking about the leaves falling. Initially, carbon dioxide is taken into the leaves for photosynthesis, if I remember correctly. They fall in the fall. It goes back into the environment. So should we be planting more trees or less trees?
Planting more trees, right? So on balance though, as a tree is growing in its life cycle, if you plant a little one, it's going to be taking up more carbon and storing it, because actually some of that energy goes into the roots and is stored below ground. So on balance, it is better to plant a tree, because over time, as that tree grows and gets big, it's going to be taken up more than it's sending back to the atmosphere. But if we have a tree that, let's say, is fully grown, it sequesters the carbon and then it drops the leaves. I think almost most of the time that the tree is still going to take in more than it loses, but there's not much we can do about the fact that these leaves are falling here right now. And unless we take that and bag up all our leaves and then dig a hole and plant those leaves in the ground, the carbon is going to go back from the leaf drop. But in general, planting a tree is a great thing to do. I like to say, drive an electric car and plant a tree. You'll be reducing your emissions, and you'll be creating carbon sinks. If we can go across the Northeast all over and plant lots of trees, that's an increasing sink. We got to avoid cutting trees down, and especially we have to be worried about what's going on in the Amazon, where they're deforesting large sections of the Amazon for grazing area for cattle. And I remember my previous point I wanted to make was about the fact that they're getting into the fields earlier. We're clearly seeing an earlier spring thaw and a later fall freeze. So the amount of time that's viable for growing things is increasing. The growing season is getting longer because of the earlier spring thaw and later fall freeze-ups. And some places in the Midwest are actually able to put in 2 rotations of crops, where previously they could only do 1. So that's one of the benefits about a warming climate, is a longer growing season, provided you're not reaching some critical heat thresholds that damage the crops.
Go ahead, Catherine.
If no one else is going to say anything, I was going to say, all in all, I think I'd rather be in the Northeast than California right now, where everything is, carbon dioxide is really heading back into the atmosphere since they're burning everything up.
Yeah, I think the problem there is going to be water resources in the future. the Owens Valley. They're getting all their waters coming from snowmelt in the mountains up to the north. And they're really going to suffer from a lack of water there as the snowpacks decline in the west. And yeah, a lot of pollution. Obviously, their air is getting cleaner, but yeah, there's not a lot. California, there are a lot of benefits of being here in the Northeast and in California with the billions of cars, certainly.
Yeah.
Yeah, and the forest fires also are very terrible west.
Go ahead, Libby, unmute yourself.
Oops. Go back.
Can you hear me now?
Yes, I can hear you. Does anybody hear me?
Yeah,
No.
can I hear you? Anyway, for those of you who can hear me, my question to you is, what can we as individuals do in our everyday life to help with this situation?
Thank you for that. That was an area of omission, not intentional, and omission on my part. So, well, first I'll say that here in this area, we're fairly enlightened, if you will. A lot of folks here. I would normally say to people, reach out to our elected officials and say that, you want to, more renewable energy, less. Here are the folks that represent us are fairly knowledgeable and know what's going on. Other parts of the U.S., then a lot of people are a little less knowledgeable, and I would say share your knowledge with people that are maybe not inclined to believe that climate's warming. Now, hopefully you folks know a little bit more about the basics of climate change and why the climate's warming. You're able to communicate that to your family and friends, some of the younger folks, help them to get inspired. I drive an electric car. It doesn't get very far on a full charge. I need to get a newer one. It only gets about 60, 70 miles on a full charge. It's kind of challenging to drive, but driving an electric vehicle, you're not, and if it's being powered by electricity generated by a solar panel. So maybe if some people are able to put a solar panel on their house, if they can take advantage of some tax credits, you're generating clean energy, sell some of it back to the grid. I get plant trees. Yeah. I think in this area, it's pretty much sharing what you're understanding and making sure your voice is heard. Some say that our governor is not doing all he could. So maybe there's some opportunity for us to reach out to that governor, or, if somebody to challenge him, and I think he's up for re-election maybe in 2 years, So making sure that our voice is heard.
Okay.
Now, unfortunately, over the past 4 years, the situation in Washington, D.C. has been rather disappointing, to say the least. It's expected that President-elect Biden will re-enter us in the Paris Climate Accord. So that's a step in the right direction. That's leadership. But in this area, we're fairly knowledgeable. So there's not so much we could do as far as our elected officials. They're in our corner.
Okay.
But sharing what you understand, sharing what you know, and trying to live. As far as demand, like reducing demand, making sure you shut off your lights. And that's part of the issue, but that really can't get us very far. To be honest, when we see what happened during the pandemic and how the emissions declined by, that tells us that we cannot just reduce demand. There's no way to reduce demand, reduce our uses of energy enough to solve the problem. That's helpful, but it's really a small part of our emissions. What we have to do is we have to bring on and hope that society embraces renewable energy, so at least our electricity uses will be generated from clean technologies that don't increase atmospheric greenhouse gas concentrations. Now, for plane travel, plane travel is necessary. we can't just say everybody stop traveling by plane. That's not going to happen. And airplanes are going to still have to use fossil fuel energy. We're not going to be able to have big batteries that power jet engines that are driven by clean energy. That's not going to happen, and shipping and things like that. So there's going to still be emissions or uses of fossil fuel going forward, but at least for our electricity generation, if we could have more renewable, more solar, more wind in the US, at least our electricity generation. So that's where we really have to focus our energy. And I would say I'm not inclined at this point to try to harp on somebody to make sure that they drive less or turn off their lights or keep the heat down to 50 degrees and 60 degrees in their house. It's really about the large scale implementation of renewable energy that's going to really get us out of this problem.
Thank you.
You're welcome. Wow, a lot of great questions and comments.
Does anyone else have a question?
It was a great presentation. Really, I want to congratulate you. It was absolutely wonderful. It was clear. I enjoyed it. I mean, I didn't enjoy what you were saying in the sense of the mess. I didn't enjoy the message, but yes, thank you. Really, really.
Oh, thank you. It was great. This was an opportunity to update my slideshow presentation. I hadn't done one of these like this in about 2 years or so. So it was a good reason to update all my charts. So now I'm ready to go. If anybody else needs a talk, I'm ready to go for the next year or so. It was a real pleasure. It was an honor to speak with you today. Everybody.
Thank you. Thank you very much.
On behalf of the Women's Club, I
Thank
would
you.
like to thank you. I'm off camera, but I'm right here, and present you with our traditional mug. So when you drink your coffee in the morning, you can think of us.
Thank you very
Thank you.
much.
And I'm just going to sit here for a minute, take my mask off. I just want to say what a fabulous program this was, really interesting. And I want to remind you all that our next meeting, I heard you talking about it before the general meeting started. It will be on Sunday, December the 6th at 3 o'clock. Lois Smith and Charlene have been working really hard to pull this all together. And it will be vocal music and some instruments. So please plan to join us then. And if you want to share this program today with any of your friends, you can find it on the website. It'll be there shortly. So thank you. Have a wonderful Thanksgiving, and everyone take good care. Goodbye.
Thank you.
Bye. Thank you. Thank you.
Thank you.
Thank you.
Happy Thanksgiving, everyone.
Happy Thanksgiving to you. Stay safe.
Yes, stay safe, right.